In number 2 on the worksheet, what we're asked to do is we're asked to find out the pressure that a certain gas will apply given a set of conditions. And in part A, we're asked to do this using the ideal gas law. And in the second part, we're asked to do it using the van der Waals equation, which is what you use when the ideal gas law isn't appropriate. So the first one is pretty straightforward. We're told that 1 mole of this carbon tetrachloride occupies 20.8 liters at 313 Kelvin. So it's just a matter of plugging in our information to the ideal gas law, which remember is PV equals nRT. We're going to make sure our temperature is in Kelvin, and solving for P. If you do that, you get a pressure of 0.918 atmospheres. Okay, in the second part of the problem, we need to use the van der Waals equation. So I've written the van der Waals equation here. The first part of this equation accounts for attractive forces. So this n squared A over V squared accounts for attractive forces. The n and the V you've seen before, right? N means number of moles, V is volume. A is something new. It's a constant, and it's something you'd look up for each gas. This second part of the equation, this NB, accounts for particle volume. So in this case, N again is something you've seen before, it's number of moles, and B is another constant. Different gases have different A's and B's, and these are all values that you can look up. So the hardest part of this problem, I think, is probably just doing the algebra and making sure you keep your numbers straight. We have all the information we need, you just need to plug it in. So plug in 1 mole for your N, plug in the A that's given to you in the problem for A, plug in 28 liters for V, and so on and so forth. If you do so, you'll start off with your equation looking like this. From here you can simplify it. So first thing I did was simplify this fraction here and simplify the numbers in this parentheses here, and the same thing with the stuff on the right side. Doing so will give you this next step. From here you can FOIL using your 27.9 liters. You'll get to this step here. You move your 0.725 to the right by subtracting it, divide each side by 27.9, and you'll get a pressure of 0.895 atmospheres. Right? It's slightly different than the one you calculate using the ideal gas law, but it's not radically different, and we should expect that, because in most circumstances, the assumptions behind the ideal gas law are actually pretty valid. Number 3 is a gas stoichiometry problem where we collect a sample over water. When we collect something over water, it's your basic gas stoichiometry problem with an added step. And the added step is that we have to account for the partial pressure of water vapor. So we know that the total pressure that we collect is a combination of this C2H2 and this water vapor. Because, again, whenever you see collect over water, it means you have to worry about the pressure of water vapor. Pressure of water vapor just depends on temperature. You're given a temperature here. You're told it's 23 degrees Celsius. You can then look up the vapor pressure of water at 23 degrees Celsius. It's 21.07 millimeters mercury. To solve this problem, we're going to need to know the partial pressure of C2H2 because we're going to need to use that in our ideal gas law. From here, it's a matter of subtracting this partial pressure of water vapor from our total pressure, which is dictated in the problem. So we've got 745 millimeters of mercury being our total pressure. If we subtract our water from it, we get that 724 millimeters of mercury worth of pressure are related to our C2H2. Okay, from here, we want to figure out the number of moles of C2H2. Again, because we want to put this into our ideal gas law, because in the end we want to solve for volume. We're starting off with mass of one thing. We're going to start off by going from mass of calcium carbide, CaC2, to moles of calcium carbide. And you do that using the molar mass. The molar mass of calcium carbide is 64.1 grams per mole. We want to divide by the molar mass here because we want to cancel out our grams. We want to know the final volume of acetylene gas of C2H2 produced here. So we need to go from moles of CaC2 to moles of C2H2. You do that using the mole ratio in the balanced chemical equation. That ratio is 1 to 1. You get, again, these mole ratios from the coefficients in your balanced equation. We arrange this so that we get C2H2 on the top, CaC2 on the bottom. Those cancel out. And given that information, right, our 0.752 grams of calcium carbide should produce 0.0117 moles of acetylene gas. This is basically, this part of the problem is something we've done multiple times in Chapter 11. Right? Go from grams of one substance to moles of another substance. Once we've figured out our moles of C2H2 and our pressure of C2H2, we can calculate the volume that this will occupy. We've got a pressure, we've got number of moles, we're given a temperature. Key thing is you got to convert that temperature to Kelvin. From here, it's just a matter of plugging everything into the ideal gas law. Because our pressure is in millimeters mercury, we're going to use a different R value. The R value that corresponds to millimeters mercury is 62.4 millimeters mercury times liter per mole times Kelvin. If we've done our math correctly, the final answer, therefore, should be 0.298 liters of acetylene gas.